So now we want to do some basic applications of three-dimensional vectors. We've already done a couple basic ones with two-dimensional, but three-dimensional ones are more complicated because you can't use a single angle to find or to show direction, not like you can in a two-dimensional case. So that makes things a little more sticky. All right, so we have an ascending airplane. It's traveling at a speed of 100 miles per hour in a direction that is 70 degrees north of due east. It ascends at an angle of 15 degrees. Find a vector to describe the airplane's velocity. Okay, so this will be fun. So we first have to think about how this is going to work on the coordinate axes. So this is the positive y-axis direction, right? And then this is z. Now z will represent up, right? So positive z is up, negative z is down. The positive y direction, if you'll remember, is north. So this is up, this is north, and this is the positive x direction, which is east. Right? West is over here, south is down there. Okay, so we have an ascending airplane traveling at a speed of 100 miles per hour in a direction that is 70 degrees north of due east. Okay, so that means that it's kind of coming out this way, where that angle is 70 degrees, and it's kind of coming that way. Right? And then you're going to go up into the air. So we want to go up an angle of 15 degrees. So let me kind of go up. I'm afraid that if I go up 15 degrees, I'm going to end up there. So let me shorten this just a little bit, just to make it make a little more sense here. Actually, let me steepen my angle too. So just to make this a little bit more clear. All right, so now I'm going to go up 15 degrees, and that's going to get me here. So that angle is 15 degrees. And this is the positive z direction, and it's making a right angle with the vector that was coming out into this space. Haha, this will be fun. Okay, so think about the two-dimensional case for just a second. So if I draw the two-dimensional, if this is your y and this is your x, and it's coming out in this direction, and that's 70 degrees, we know that direction piece, right? We know that vector. That would be the cosine of 70. Sorry, cosine of 70, sine of 70. If we were only dealing with two dimensions. But we're not, but that's how it would work, right? Okay, so now how can we deal with the third dimension? Well, the easiest way is to imagine that this vector right here is a unit vector. So it has a length of 1. We'll deal with the 100 later. So we're going to make this be a unit vector of length 1. And therefore, the tangent of this angle, 15 degrees, is opposite over adjacent. It is z divided by 1, or just z. So that means that my vector, if you will, my foundation of my vector, it's not actually my vector, but my vector would be cosine of 70 degrees, sine of 70 degrees, that'll get me this component, and then tangent of 15 degrees, and that'll get me my lift. Now, there's a problem with this, which is this is not at all the speed we want. We want a speed of 100, and we also assumed a unit vector right here, right? We assumed this was length 1. Okay, so how do we make this a unit vector? We know this is the bare bones of what we want, but we got to make it a unit vector. So we're going to have to divide it by the magnitude of itself in order to unitize it, if you will, right? Instead of being whatever length this is. We don't know what length that is, but whatever length it is no good for us. So we're going to divide it by the cosine of 70 squared plus the sine of 70 squared. Those two would make 1 together, so they're not a problem. Plus the tangent of 15 squared. And those are all degrees. That will make the basic directional vector that I want the length that I need. So I'm going to make it a unit vector. Okay, so this is a mess. We obviously need some decimal approximations here. So we can do this with Desmos, we can do it with Maple, whatever makes you happy. I'm going to do it with Desmos, I think. So I'm going to start by finding in Desmos a equals, and I'm going to find the square root of cosine, oh, I better make sure I'm in degrees. I don't think I am. Oh, I wasn't. There we go. Click to degrees. Cosine of 70, and then I want to square that. You can do that by putting, I believe, the squared in here. And then plus sine squared of 70. See, that would be just 1. That wouldn't be a problem. But then the tangent squared of 15. And there we have it. It's 1.03. So now what I'm going to do is I'm going to take the cosine of 70. I'm just going to divide it by a, that value. And then I'm going to take the sine of 70 and divide it by a. And then I'll do the same thing with the tangent of 15. And we learned in the last section we could do this with Maple as well. We would just have to convert all our angles to radians to make it work. All right, so there we have our values. We can see that it's 0.330, 0.908 if you round it, and 0.259, roughly. Okay, but that's not the length of 100. This is a unit vector. Its length would be 1. Right? That's the whole point. So this is length 1. Now, how do I make it so that the speed is 100? Well, what you do is your vector v is 100 u. So you just take 100 and you multiply it by each of those pieces. Which of course would turn it into 33, 90.8, and 25.9. That is a vector that is magnitude 100, right? So the length on this one is 100. And it's in the direction and with the lift that we want. So it's in the direction of 70 degrees north of due east, and it has a lift of 15 degrees above the horizontal. All right, so now we have a golf ball is hit with a force of 2,000 pounds at an angle of 60 degrees to the horizontal. If the golfer accurately aimed at the pin, which was 45 degrees northwest of him, find a vector that represents the force at the moment of impact. Well, there's that force piece again, right? Okay, so let's think about this here. We have this is east, this is north, and they're going to go northwest. West is over here, so there's west, and they're going to go 45 degrees northwest, so that means they're shooting off into that piece right there. So they're going right there with a 45 degree angle right there. Or if you will, it's really 45 degrees here. Let's leave it there. It's that technically both of them are 45, but I have my reasons. So 45 degrees northwest. Okay, so then find a vector that represents the force at the moment of impact. Okay, so we need to deal with this angle. So I've dealt with the 45 degrees northwest, right? But now I have to deal with this angle of 60 degrees to the horizontal. So what that means is that it's going to, right, that's on the flat plane. And then we're going to shoot up into the air 60 degrees. Okay. Now, this component that's on the xy axis, that we know would be cosine of something, sine of something. Now, notice I'm not saying 45. Why not? Well, because we're not in quadrant 1. right? 45 degrees is in quadrant 1. It's over here in the northeast corner. But we want the northwest corner. Ah, okay, so that's not 45. That's 45 right here or 45 right here, but that's not how we measure angles. We always measure angles from the horizontal, positive x-axis, which in this case is the east. So that would be 135 degrees. And so that's the number we put here. Right? Because we're working in quadrant 2 here. Okay, so it's the cosine of 135, sine of 135. That's going to get us our direction. And then we need our lift. Well, the lift is coming from the angle from the horizontal, which is the 60 degrees. All right, so that would be the tangent of 60 degrees, right? That one's pretty easy. Okay, so let's think about the unit vector. It's going to be cosine of 135, sine of 135. Oop, not 153. I was about to have a little dyslexic moment there. 135, and then tangent of 60 degrees, right? That gets you the vertical lift. Or if it's going down, you can have descent, but this isn't ascent. This is climbing. Now you have to turn it, so this is the bare bones of what we want. This is kind of heading in the direction we're looking for. So if you will, I can say this is the direction. Here, let me put it this way. Actually, I don't want to do that, just because I want to get space. So this component, these vectors, get us our direction and heading. Right? Our direction and our lift is taken care of. But it's not the right size. Right? So we're going to make it a unit vector to get to the right size. So we want to take this vector that we've got, and we want to unitize it. We want to make it have a length of 1. So we're going to divide it by the cosine squared of 135 plus the sine squared of 135 plus the tangent squared of 60. It's just easier to write it that way. And then we're just going to make Maple do it, or Maple or Desmos. I suppose it doesn't make any difference. I'll use Desmos because I just used it. Okay, so I can actually redo this. So this is 135 is my angle, and 135, and then 60. Make that bigger. All right, so then I want the cosine of 135 divided by that, the sine of 135 divided by that, and then the tangent of 60 divided by that. So I have those values. So lovely. Let me write those down. So negative 0.354, positive 0.354, and 0.866, which is definitely a known value, but we don't have to worry about it. Okay, so I now have my unit vector. This is length 1, right? It's going in the right direction, it has the right lift, and now it's a length of 1. So direction and lift are taken care of up here. Dividing it by the magnitude makes it length 1. And so my v vector, what I was actually looking for, oh, my force vector, sorry, this isn't velocity, this is force. So sorry. Force, it's the same idea, but the math behind it's the same, but the idea behind it is very different in terms of physics, I'm sure. So we want 2,000, right, because that's our magnitude, that's the force, right, 2,000. So we want 2,000 U. So we were just going to multiply each of those numbers by 2,000, and again, we're just going to make a computer program do that. That's not something we're going to do by hand. So I could just multiply 2,000 times each of these. I don't even know if I needed to do that. 2,000, yeah. So 707, so negative 707, positive 707, and 1732. And there we have it. I don't know if they said, oh, this would be pounds. Oh, I should have left a little space. Because it's a force vector, it'll be pounds. Technically for each of the units, but you can just kind of write it at the end. Sorry, that came out weird.